Hello. For section 10.5, we're looking at polar form of complex numbers. So a complex number is going to be z equals a plus bi. That's rectangular form, but we are going to convert that rectangular form into polar form in a little while. But first, let's look at how we would graph a point in complex form. Okay, so we have the horizontal axis that represents the real part. So that would be the real part, which is the A. And then we have the vertical axis, which represents the imaginary part, which is the B. Okay, so let's plot a point, a complex number, in the complex plane. Notice that the complex plane has the real axis instead of the x-axis and the imaginary axis instead of the y-axis. Otherwise, it's pretty much the same as the rectangular coordinate system. So when you're plotting a complex number, you're going to go 2 in the real direction, which is to the right, and then -3, which would be down 3 units. So it's going to be right there. That's how you would plot the point. 2 minus 3i. 2 to the right, down 3. Okay, let's move on. So now we're going to look at how to convert from rectangular form to polar form. So let's look at that. So the first formula that they give us is the absolute value of z, which is the absolute value, which is also known as the modulus of a complex number, is given by the square root of x squared plus y squared. Okay, so let's find the absolute value or the modulus of this point in this next exercise. Okay, so we have x equals radical 5. We have y equals -1. So the absolute value or the modulus is going to be the square root of 5 squared plus -1 squared, which is going to be 5 plus 1, which is the square root of 6. So that's known as a modulus. Okay. Okay, now let's go to the next page. Okay, so now we're going to write a complex number in polar form. So that's the next thing that we're going to learn in polar form. So we're going to need the modulus, r, and we're going to need the argument, theta. Those are the two things that you will need in order to be able to write the complex number in polar form. So here are the set of formulas that we already know from previous sections. X equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared. Notice that's the modulus formula. And tangent of theta is equal to y over x. Okay, so here is the official definition of a polar form complex number. So it is right here. Z equals the modulus, parentheses, cosine theta plus I sine theta. You can also write this in the abbreviated version, which is RZ equals R cis theta. The cis stands for cosine plus I sine theta. All right, it's just a shorthand. So let's express the following complex number 3i using polar coordinates. So we need to find two things. We need to find r, the modulus, and theta, the argument. Okay, so let's start with r, the modulus, which we already know the formula up above. It is, well, first let's identify x and y. X is 0 because there is no real part, and y is +3. Okay, so the modulus r is given by the square root, x squared plus y squared. In this case, it's 0 squared plus 3 squared, which is the square root of 9, which is 3. Okay, so we have the modulus. Okay, now let's find the argument. The argument is given by tan theta equals y over x. In this case, we have tan theta equals 3 over 0. Well, that is an undefined value, right? You cannot divide by 0 in math. So if you think about that, on the unit circle, where is tangent undefined? Well, it's undefined when y is 0 and x is 1. That would be at pi over 2. So if you look at your unit circle, you will see that theta is undefined for tangent at pi over 2. Also 3/2 pi, but that's why it's important to look at this, this original number. If you were to graph that in the complex plane with the real and imaginary axis, you will see that the point is up here, 0, 3. And so we know that it's got to be in the upper half of the unit circle. And that corresponds exactly to what pi over 2 is. So that's how you know it's not 3/2 pi instead. Okay, very good. Let's continue. Oh, we haven't completed the problem. We still have to express it in this form up here. As you can see, this is how you write a complex number in polar form. So let's finish the problem off. Whoops, that's not what I wanted. I wanted the pin. Z equals R, which is 3, cosine theta, which is pi over 2, plus I sine theta. Or shorthand, Z equals 3 cis pi over 2. So you have the choice. You can use the abbreviated version, or you can just keep it the long version. Either form is fine with me. Okay, let's do another example. So what I recommend is first identify the quadrant in which this point is on the complex plane. Well, as you can see, x is negative and y is positive, so that would be quadrant 4. So x, whoops, that's not what I wanted. So we got x equals negative 4, y equals positive 4. That is quadrant. That is going to be quadrant 2. So we know our point needs to be in quadrant 2. Okay, so let's start with the modulus. R equals the square root of x squared plus y squared. That's going to be the square root of 32, 16 plus 16. We can simplify that. That's going to become the square root of 16 times 2, which then becomes 4 radical 2, because 32 is the square root of 16 times 2, and the square root of 16 is 4. So that's how I got 4 square root of 2. So that is our modulus. Okay, now let's go on and find the argument, theta. Tan theta equals y over x. In this case, we have tan theta equals negative 1. On the unit circle, if you go to quadrant 2, you're looking for the angle that has a tangent value of negative 1. And that angle, if you look at your unit circle, is going to be 3/4 pi, because it has to be in quadrant 2. Okay, so theta equals 3/4 pi. Okay, so that is done. Once you have the modulus and the argument, now you can go ahead and write your final polar form version of that complex number. So R for radical 2 cosine 3/4 pi plus I sine 3/4 pi. And of course, you're welcome to use abbreviated version if you like that better. Okay, let's continue. Okay, so now we're going to go in the opposite direction. We're going to go from polar form to rectangular form. Actually, that's the easier way to go. So let's take a look at how you would do that. As you can see, we have a polar form complex number, and they want us to convert it to rectangular form. So it's just a matter of evaluating cosine of 30, sine of 30, and then distributing the 12. So that's all you really have to do. So it's easier to go in this direction. So let's write this out. 12 cosine of 30 from the unit circle is square root of 3 over 2 plus I. Sine of 30 on the unit circle is 1/2. Okay, and now all you got to do is distribute the 12, and then you are done. So z is equal to 6 square root of 3 plus 6i. As you can see, 2 goes into 12 6 times. So I just simplified the 2 and the 12, and that's how I got the 6. Same with the 1/2. 1/2 times 12 is 6. And don't forget the I. Okay, that completes this problem. Okay, let's continue down. Okay, so now we're gonna work with two complex numbers. As you can see, they give us z1 and z2. They're both in polar form. So they're gonna ask us to multiply to find the product of those two complex numbers. So the formula to multiply two complex numbers that are in polar form is to simply multiply the moduli, which are the r's. You multiply the r's together, and you add the arguments. So we're going to add the arguments. All right, so if you add the arguments, you're going to get theta 1 plus theta 2 for the product. Theta 1 plus theta 2. And when you divide two complex numbers that are in polar form, you're going to divide the moduli, divide the r's, and you're going to subtract the arguments. Subtract the arguments. So it's going to be theta 1 minus theta 2, theta 1 minus theta 2. Perfect. Okay, so that's the formula. Now let's apply those formulas to this example. So we have two complex numbers in polar form, and they're asking us to find the product. So the product means we're going to multiply. So let's apply the formula. So we're going to do z1 times z2. That means we're going to multiply the moduli. So that's going to be 4 times 2. And then we're going to add the arguments. So cosine of 80 plus 145 plus I sine, same thing, 80 plus 145 degrees. And that should take care of that problem. So after you multiply the moduli, you get 8. And when you add the arguments, you should get 225. And that is it. So it's pretty simple to multiply two complex numbers when they're in a polar form. It's actually easier to multiply them when they're in polar form versus when they're in rectangular form. Okay. Now let's look at the next exercise. They want us to divide. See the quotient. They're asking us to find the quotient. Quotient means to divide. So we're going to apply the other formula. The other formula was to divide the moduli. So that's going to be 2 divided by 4. And now we're going to subtract the arguments because we're dividing. Okay, once you do that, you should end up with 2 divided by 4 is 1/2. Cosine 213 take away 33 is 180 degrees. And that will do it. So that's what we got to do when we're dividing. Okay, let's turn the page, and there are a couple more formulas for us. This one is called De Moivre's theorem. It's raising a complex number to a power. So if you're raising a complex number to a power of n, then what you want to do is you want to raise the moduli, or I'm sorry, the modulus to the power of n, and you want to multiply the argument by n. So it's just a matter of raising the modulus to the nth power and multiplying the argument by n. So that's what we're going to do here. So n times theta, n times theta. Okay, so this following exercise, notice that they give us a rectangular complex number to the 5th power. So we're not able to apply this formula yet. Before we apply the formula, we have to convert this complex number to polar form. So let's do that. We did that earlier in the section. So x is 1, y is 1. That's quadrant 1. Okay, let's find the modulus first. Square root of x squared plus y squared, which is going to be the square root of 2. All right, so we got the modulus taken care of. Now let's find the argument. All right, tan theta equals y over x. Tan theta equals 1. Because we're in quadrant 1, if you look at the unit circle in quadrant 1, you're looking for the angle whose tangent value is 1. You will see that it is pi over 4. Okay, so we got the argument. Okay, now we have the number written in polar form, which is exactly what we wanted. So now let's go ahead and raise it to the exponent. Okay, so we got z equals square root of 2 cosine pi over 4 plus I sine pi over 4. Now we can raise it to the 5th power. That means we're raising the modulus to the 5th. And recall that we're multiplying the argument by 5 as well. So because n is 5, you're multiplying the argument by 5. So pi of 4 times 5 is 5 fourths pi. That's where I got the 5 fourths from, because I'm multiplying the argument. Pi over 4 times 5 gives us 5 fourths. So whatever the exponent is, that's what you multiply the argument by. Okay, so now we have plus I sine 5 fourths pi, close parentheses. Okay, they do want us to write the answer in, rectangular form, because the problem was given to us originally in rectangular form, so our answer should also be in rectangular form. So we're not done. We have to evaluate using the unit circle, and then we have to distribute, and then we're done. Okay, so let's evaluate these. Using your unit circles, you should be able to evaluate those two, and you should get radical 2 to the 5th. The cosine of 5 fourths pi is negative radical 2 over 2. And the sine of 5 fourths pi is also negative radical 2 over 2. Okay, and so now we distribute. Okay, when you distribute, you have you're multiplying powers with the same base. So what you're going to do is you're going to add the exponent. So if you have radical 2 to the 5th times radical 2 to the 1, that's going to be radical 2 to the 6th. So you're going to have negative radical 2 to the 6th power over 2. And then over here, you're going to have the same thing. Okay, so I'm just adding the exponents. All right, and if you raise radical 2 to the 6th power, that's actually going to just be 2 to the 3rd. 2 to the 3rd. So you're going to have negative 2 to the 3rd over 2 minus I 2 to the 3rd over 2. All right, and now you can subtract exponents since you're dividing, so you should get negative 2 squared, which is negative 4 minus 4I. So that is our final answer. Okay, so that type of problem requires quite a few steps. You first have to convert the polar form complex number into, the rectangular form complex number into polar form. Once you've done that, then you can raise it to the 5th power using de Moivre's theorem. Okay, let's move on to the last problem of this section. Okay, here it is. It's finding roots. So we're finding roots of polar form complex numbers. So here's our formula. As you can see, the nth root of a complex number is the nth root of the modulus. And then the argument, you add 2k pi and divided by n. All right, and then you can substitute these values into k depending on how many distinct solutions or roots you're looking for. In this example, they're asking for 3 distinct cube roots, so you'd have to plug in 0, and then 1, and then 2 to get the 3 distinct roots. So let's go ahead and apply this formula. So let's start off with z to the 1/3 power, because that's the cube root. Z to the 1/3 power, because that's cube root, is 1/3, is equal to 8 to the 1/3. That's what the formula says. Cosine. All right, so theta is 2/3 pi, so we have 2/3 pi plus 2k pi divided by n. N is 3 because it's a cube root. And then same thing for the sine. 2/3 pi is our argument plus 2k pi divided by 3 because it's a cube root. And that should do it. Okay. Now to evaluate, like I mentioned earlier, you have to, since they want 3 distinct roots, you have to substitute k equals 0, and then we'll do k equals 1, and then we'll do k equals 2. So for the first one, we are doing k equals 0. All right, so let's do that. So when you plug in 0 for k, you should get the cube root of 8 is 2 cosine 2/3. Well, this is just going to become 0 because k is 0, so this will disappear. You have 2/3 pi divided by 3, which is 2/9 pi. Okay, so that's the first root. So that one's complete. Now let's do the next one when k is equal to 1. So when k is equal to 1, you have to do a little bit of arithmetic on the side. Plug in 1 for k, so that's 2 pi plus 2/3 pi. If you do that on the side, 2 pi plus 2/3 pi, you should get 8/9 pi. Okay, I'll let you guys do that on the side. So I'm just going to go ahead and write the solution for that. It's going to be cosine 8/9 pi plus I sine 8/9 pi. I'm going to let you do the work where you plug in 1 for k. So you have 2 pi plus 2/3 pi divided by 3. You should get 8/9 pi when you do that. All right, for the final third cube root, you're going to plug in 2 for k. And same situation where you're going to plug in 2 this time. And for k, so this is going to be 4 pi. 4 pi plus 2/3 pi divided by 3. I'll let you do that work. Is going to be 14/9 pi. So let's write that out. Okay. And that will complete this section.